Okay, so hi guys, welcome to the workshop. So the plan is to keep it a hands-on workshop more rather than a presentation. So yeah, so I'll get started with the workshop. So I guess some of you must have seen what the navigation stack is actually, and you must be having an idea of what it is. So if, for the uninitiated, I'll just show you what it is, and I'll show you how amazing it is. What an amazing open source code ROS has provided to us that we can easily deploy on any robot, right? So this is the wiki page that comes up. You can just have a read through it whenever you want, and there's some tutorials which you can have a look at. And the main code lies here on this GitHub page, right? So if you look at this, it's an amalgamation of multiple packages, right? Like you have what are the various things you come when a bot is moving autonomously. Number one, it should know where it is, right? Number two, it should have an idea of its surroundings, and finally, it should be able to find the shortest path uh, between where it is and where it's supposed to go without colliding with any obstacle which may have already been there, like a static obstacle or a dynamically moving obstacle, right, which may move around in its path, right? So looks like it was down, and maybe I'll just go through this thing. Okay, we'll come back to it later, I guess. So I'll start with the workshop. I'll show you how amazing it is and how easily you can get started with it, right? So first, I'll show what we'll be achieving today, what we'll be learning today. Before I move on the details of how you can modify things and tweak things according to your purposes, right? So firstly, I'll spin up my world and as you go inside, right? So as you can see, so what we have today here is a good old husky, right? A four-wheel robot. Uh, then this is our world, we have walls, and as you can see, husky is surrounded by these blue rays, which are is something with the lidar, right? So it has a lidar on it, and one of the most essential things of the Snapstack is that it needs a lidar, right? Without which it's one of the core fundamental things of a Snapstack, based on which everything is written, right? So if you don't have a lidar, then you have to come up with other techniques, right? Like of localization, because the entire abstract depends on localization and through the lidar, right? Because it's very accurate. And so for our purposes now, we have husky with a lidar on it, right? So if you see right now, I've just spawned the world and husky inside, right? Just forgive me for that. No. Yeah. So and here we have Arvis, right? As of for now we have nothing because we don't even have the map frame right now. So everything is having an error state, right? So now I'll just spawn up the other things. Yeah. So immediately you can see that for once we have the map frame, right, because now we don't have an error anywhere. So which technically means that the robot is connected to the map frame, right? And the laser is connected to the robot, of course. So as you can see right now, that you can see a partial map, right? You cannot see a full map, right, of the surroundings, but you can see things are somehow somewhere around like this only. There's something to the left, something ahead of it, right? This is more or less pretty accurate. And but why is it partial? Because of course the LiDAR rays are not reaching the far points. Right? It has a LiDAR has a fixed range, right? So as you start moving around, the map will start getting more of the map will start forming, right? So coming to the point, now say you have this, right? Now the magic will start, right? I can just give Husky a goal point anywhere, any random point anywhere. I know this exists in the map, right? I know this exists in the world, so I can just give it a point here. Save, and you will see that as Husky moves along, it will create the map around itself. Right? I can give it a point, say here, and you will see that more of the map will get formed. So this entire navigation that you're seeing right now, this all these red, this green line bar that you're seeing, these red small lines that you can see, right, everything, this all comes under the nav stack, and this entire thing is happening autonomously. I have done absolutely nothing other than setting things up correctly and just calling them in the launch file. Okay, so if I give points here also, you can see then these also will start forming up. So if I just check if it's there in the world, yeah, it's there. So let's give it a point somewhere here maybe, and it will find out a way by itself while creating a map on the way. Right, so it's compute. So all this computation is happening online, not offline. Right, it's computing the path, checking for obstacles, recalculating, and then finding the optimal path at all times. Okay, so it's formed a wireless board map, right, by itself. So far, I've just given it points and it has gone around and found out and formed the map by itself. So this is one of the most crazy things about Napstack, that it allows you to do this by just writing 20 lines of not even code, of writing 20 lines of YAML files. So I'll just show you how I got this done right first before I move ahead. Then I'll show a different implementation of Napstack where you have a fixed map and you are navigating the robot inside the fixed map. Okay, so this one is a dynamic approach and it has drawbacks. Right? There are cases where the bot can get stuck. You have to tweak it a lot to get it to moving the way I have done it here right now. Like it took a lot of effort. It took a lot of tuning. So those are the drawbacks. So coming to the files, right? So the structure of the what I'll just show you the this is my Catherine workspace, right? My source file. This is the folder we're working on, the package cam. Right inside that we have our models inside the Husky robot inside this, and all the world files inside this. Right. Then that's it to get started. So coming to the first thing, the thing start from is the robot model, right? All the frames and everything is defined there. All the laser frames, all the camera dash, maybe everything, the gazebo references, the sensors, everything is defined in first inside the audio. So it's the start point of your project. So for that, let's look at the ORDF, right? So this Husky URDF you can just get online. If you search for the Husky package, you can just find this URDF. What you need to tweak here, or you might need to tweak it, are these frames. These frames also you won't need to tweak, right? If you're adding some new frame, you obviously have to do that. Apart from that, the main uh, the main thing is this, right? I'll just show you things that make a difference in the configuration, which is this. Wait. Yeah. So we have the laser link here, right? All these are predefined. It's all there. This URDF is entirely open source, right? So you have this link named laser, right? Just another normal link. What makes it special is this gazebo tag, right? Yeah, this gazebo tag. At this also you can just search online and you will find gazebo plugins. Okay, my net is getting slow today, but in this uh, on this page you will find all the plugins, right? You can find all the plugins, the camera, GPU, lasers, depth camera, everything you can get, right? You will get this exact snippets of code here, right? So again, these you don't need to tweak, right? These are already there. These are based on the real hardware modules that you have for lasers. What you will have to concentrate on in simulation is this topics, right? So you have the scan topic and the frame name. Frame name is just the name itself. So this topic is the most important thing, right? And that is that, and it's attached to the laser link, right? The name of that link has to be put in here, and the topic name is here. That's it. That's it for setting up the lidar on your robot. Okay, with any robot, you can just set it up as easily as that. Uh, And apart from that, there is another thing. This right. So, like any robot, like if you have taken part in Technics, maybe then you must be knowing how a differential drive works, right? So differential drive works for two wheels, right? It works for two-wheel robots. What if there is a four-wheel robot like Husky in our case? So there are multiple controllers written already for that in Gazebo. So you can have there are two three controllers that you can have, right? You can check it on the Gazebo plugin page. One of them is skid steer drive controller. This is exactly what we want for Husky, a four-wheel drive robot, right? Where you can control the four wheels. It's called a skid steer drive controller. This is exactly all the physics behind it, all the mathematical calculations have been already done by someone, and they have put it in the form of a plugin. You just have to call in, and these are the parameters of this plugin, right? You just put in the wheel joints. You put in all the wheel joints, and these two the parameters like wheel separation, wheel diameters for correct mathematical calculations, right? And the robot base frame. The base frame of the robot, everything is defined with respect to robot base link, right? Right at the beginning, you have everything defined with respect to robot Husky robot model basing. This is the base thing of the robot, right? If you know about the RDFs, you must be knowing what the base thing is, right? So coming back, so everything set up with respect to the robot base link. This is a very important parameter to come up everywhere, right? And another important thing is the velocity topic, right? So at the end, these you can control the wheels, right, on the basis of the velocity of this velocity command, right? And so basically, what this plugin does is, what this plugin actually does, you given a you tell the bot to move at a certain velocity, linearly, and you basically give it a linear velocity and an angular velocity, right? That's what we feed in, and what this plugin will output will output the velocities of all the four wheels in order to achieve that. Right. Internally, it will do all that, and you'll have the robot moving as you want it. So all you give it is a linear velocity and an angular velocity in your world frame, and it transfers that to the velocities of all the four wheels. That's what this plugin does entirely. So for that, you need to give in the velocity topic from where you feed in the velocities, right? And the odometry topic and odometry, that is for the purposes, right? When you're calculating, like when you're having a rough estimate of where the robot is by integrating the velocities, right? You can find out the distance, right? That is what odometry does. So it adds up the velocities over time, and that's what you have as the as a as a rough estimate of the robot, which will work. It will work in simulation, right? But in real robots, encoders are always they always have some drift, and the drift over like basically drift over time, and inaccuracy increases, right, over time. So, but it's important for our case in robotics, right? We always have an odometry frame, which we keep on correcting with respect to some source of absolute truth. So this is the plugin that I want to introduce you to. So if you see, if I just spawn the robot, right, and in a separate terminal, I just do maybe ROS and tell you just right keyboard. Yeah, I can drive the robot now easily using I. Right, I is for forward velocity. Stop it. To turn it, I'll have to give L and J, yeah, and K to stop it, right? So this entire part is done with the help of this plugin here, without which even this I cannot accomplish, right? If I just comment this part out, then you will notice that I comment this part out, I spawn it back again, and you will see it won't run. See, there is no topic called CMD velocity, so you cannot control the robot at all. So this is just from where things start, right? The absolute basic you're done with here. You can control a robot by adding these lines itself, right? You can given the velocities and you can control it even in real life. Okay. Now apart from that, so we're done with the ODF. All the ODF has it has the laser and this part with extra, which you can modify. Right? The topic names you can modify and give as you want, but be careful that the packages also you have to feed in the same topic names. So these are very important. Don't mix them up. Okay. So we're done with the RDF. Now coming to the launch file. The first launch file I was launching all this while. The world file you can just see it's very basic. It has nothing. It has all the arguments for the gazebo, right? Launching the empty world and this world. Then you're launching the robot. You're launching the robot, right? Inside this parameter robot description, you do not change this. This is used internally a lot of places. So you do not change it. This is what it is. You have to use it. Then this is the package for the joint state publisher. Right. What this does is it publishes the joint states basically. I mean, if you want to have a look at what it does, you can just have a look at the topic called joint states. You can just see what the output of that is by echoing it. Right. This guy here, what it does is, as I think most of you might be knowing, that it basically in RBase you can visualize a robot in that way only. It basically defines all the joints of the robot with respect to the base link. Right. So in RBase, if you are seeing the robot model, it is due to this. If you comment this out, you won't be able to see that. Then this is we are spawning the robot right here itself, and RBase we are also calling it here. Yeah, we are launching RBase there itself. So that is it. A very basic old plain launch file, which you must have already come across. Right. Now coming to the part where things are interesting. The second launch file that I launched, right? What do you see it as two launch files? One for Gmapping, one for MoveBase. So I'll just quickly quote what they are. What this does is it launches both, right? So in Gmapping, if you go to the first file, so this is a simple node, another ROS node that you're launching, right? What is it? Gmapping. You have to install this package, right? If you're installing the entire navigation stack, this will already be there. But if you're missing any of them, or you can just go ahead and install one by one. It's fine. You can just sudo apt install Gmap ROS Noetic Gmapping, right? Or you can just download all the entire navigation stack from GitHub and make it. Cat can build it in your own workspace. Both work fine, right? Both work fine, absolutely. Uh, so coming to Gmapping, this is all. Just launching this single ROS node over here and doing nothing else, right? As you can see, it's not even code. It's just about tweaking parameters. Process mostly about tweaking parameters if you're working on pre-built packages, right? So Gmapping has some basic parameters. One of the most important ones for setting things up correctly are the base link. Again, if you see the base link, I told you it comes right from the URDF base link, right? ODOM frame comes as ODOM itself. Most likely, in most cases, you have to keep it ODOM itself, right? You can change it in basis, yeah, but again, you have to make changes everywhere. So just keep it ODOM to be sure. Then these are all these parameters you can check up on ROS Wiki, right? You can go up and check the ROS Wiki for Gmapping and you'll find all these parameters and what exactly they do, and what they mean, what sigma means, what common size means. You can get it all on the ROS Wiki page, right? And you can tweak them accordingly. But in most cases, you don't really have to tweak these values, so it works fine with it. Then coming to the main part, so yeah, this entire thing you can get online, right? You can get in the Gmapping package in the ROS Wiki page itself. So that's it about this one. Then another thing to take care of is the scan topic, right? The scan topic again comes from the UIDF, right? The scan, what is scan topic? Scan topic, I think by default here it's scan. This came from the UIDF, right? Cool. So we're done with Gmapping. That's absolutely nothing. Now we're coming to MoveBase. If CS is an even smaller file, and again the same thing here, we just have a single ROS node that we're launching. So I just launched two nodes and you saw what I was able to accomplish with that. That is the power of ROS. That is what you're going to use, and that is where we're teaching ROS every year, so that using these you can build something better. Right? So coming to MoveBase, you can improvise on algorithms, you can make new algorithms. The entire framework is there. You can improvise anywhere you want, and you can even if you are just a beginner, you can get things started with you can just get started on with things really quickly, even with a real robot. Right. So for MoveBase, coming to MoveBase again. So now what exactly is MoveBase? So I didn't even tell you what exactly is Gmapping. The entire autonomous navigation, the path planning, no, not exactly the path planning, the part where the map was getting created, right? Where the map was getting created, that exactly is Gmapping. I'll leave it to you to study more on what Gmapping is and SLAM is, right? I think you must have done it in the summer camp, right? So so I leave it here itself. Coming to MoveBase is more specific towards loss, right? Gmapping is a very common algorithm, but MoveBase is very specific towards loss. So what it does is, uh, It works on top of these of G mapping basically. What it does is we have planners as a part of this package, right? There are multiple planners, right? One is this one which I've used here, the TAB local planner. There are more planners like DWA planners. There are planners which is like Dijkstra. There are planners which is something else, right? There are so many algorithms, and no algorithm is the best, right? Algorithms differ according to the kind of robot you have, according to the type of controllers that you're using. So you have to tweak different planners, and you can just and you have to see that which one is working the best for you, right? So for instance, Husky actually performs very badly with the DWA planner, right? It actually performs very badly. This is the best planner which I have found from my experience, which works on Husky. So what are these? Right. Then coming to the next part. Right. So we're done with this, right? The planner I'm using is TB local planner. So you can find out all the parameters that it has. You can go through everything. You can study the algorithm it uses to do this planning. You can find out the performance of TAB there itself. Right. Uh, Now you can just move this package. It has a few parameters. Right. What are they? It needs some param files for building the cost maps. Right. They have to take on the cost maps, global cost map, local cost map. I won't go too much into details and bore you, but just remember that these are what this is exactly. These are the few things you need to start with things, right? And these are, and all of this you can get in the navigation package itself, right? Just have to tweak these errors return by itself, and I'll show you where the files lie. These files are actually inside the config file, the config folder here. So what exactly do we have here? Config folder. You see 1, 2, 3, 4, 5, and 6 files, right? So 6 files, all of them here. So these are the few parameters which you have to tweak for tweaking these parameters can result in a drastic improvement in performance. In a drastic, it can change the behavior of how the robot is behaving in unknown environments. Whether it is moving backwards, whether it always moves forward, whether it can come backwards if it gets stuck, whether how fast is its response rate, how frequently it is changing its local plan to keep itself on the global plan. For those who do not know what is the difference between global plan and local plan, a global plan is basically if I give you if it is a huge map and if I give you 2 points on it, right? So you have to be finding the shortest part between them, right? That is the global plan. But this then you divide this global plan into small parts, right? In small parts, and your the local plan the local path is the current path between value r and the next part of the next point of the global plan, right? So basically, like say if you're going to Varanasi, say in Varanasi you're going from it basically tells you the next 2 3 steps you have to take to keep yourself on the global plan. That's basically what local plans are. So there are different parameters for each of them, right? And they differ based on the planner you're using, right? For TB plan it's different, for DW plan it's different. So this is a local planner here, and for the global planner, these are Cosmo parameters. What are Cosmo parameters? They are basically that these are like the map that you see, right? Let's show you the map once more. This map that you see here, these pink lines, right? These white, these black portions around these pink lines, these white parts, these entirely white parts, like all of these are part of the occupancy threshold, right? So they're basically probabilities. So uh, like these are parameters that like the inflation rate is like for how far you should be away from an obstacle, like how far should an obstacle how much should an obstacle be inflated so that you do not collect it safely, right? What is the safe distance of an obstacle from a certain probability of hitting it, right? So you can think of it as that. So if I increase this value, then you will see these become more pronounced, so the robot will try to avoid going closer to them, right? That is what inflation radius is. Similarly, these are all cost parameters, right? Then you have cost scaling factors, that how much like how much should you fear these obstacles, right? If I lower the value, Just a second, sorry. If I lower the value, the robot will move closer to the obstacles. If I increase the value, it will move far. If it will always remain, try to remain far from the obstacles around it. Then similarly, then these are some basic things. This is nothing. The footprint is basically for the length and breadth of the robot. Like if you are taking the origin of the robot, the middle of the robot to be 0, 0, then these four coordinates is the footprint. Right, the rectangle that's the footprint of the robot. So for circular robots, the footprint is circular, where you put in the radius. For rectangular robots, you put in the four coordinates. So there are some parameters that you have. Apart from that, this we already covered. Again, these are the local planner parameters that specify the maximum velocity it can move linearly, right? The planning, the velocity calculations shouldn't be. So basically, what happens is first when you're giving it a navigation goal, right? First, the global plan is calculated, right? You have that long green line that you saw. You have the global plan. Then uh, then you have a local plan, like from where the current the robot is to the next step of this global plan. What should be the velocity you should feed it in, right? So that it moves according, so that it moves as much as it can on the global plan. So that velocity is calculated, right? And this velocity is calculated by this local planner. So here you see these parameters that specify that the maximum velocity of the robot should never cross more than this, and the minimum should also never be more than this. Right. So minimum should also be never less than this. So try to keep it in between them while calculating the command velocities. Right. Similarly, for the this is the linear part, then for the angular part of the velocities. Right. So if you want the robot to move in both directions, you will have a negative value and positive value. So that's that. You can also limit the acceleration values of the robot. So if the robot is shooting very quickly, you can limit that as well. You can then these parameters specify that if you're giving it a 2D nav goal, right? It's like if I'm giving a 2D nav goal right now, so if I give a point very close to a robot right now, then it won't move towards it. Okay, this move why? Because you can tweak this parameter. This exact parameter is this thing. So if the current robot, if the current position is within zero point 0.1 meters of where I'm giving it, so it won't actually care a damn about it. It won't move. Okay, it will only move if distances of the between the current position and the final target position is more than zero point 0.1. So that's the tolerance values that you can set for X, Y. Then similarly for your like the orientation, final orientation and the current rotation should also have a difference of more than this for the robot to actually start planning. Okay, so these parameters you have. So the velocities you can control, acceleration you can control the tolerance level of the goal. You can see if the robot is holonomic or not, right? Then these are not very important. Apart from that, you have move based params like move based you can call it as a bird's eye view of all the things that are going on under it, right? So the controller frequency is the mastermind. Movement is the mastermind, you can think of it, and the frequency at which it is calculating this entire, then all the command velocities, all the global bands or the local bands, right? So if you give it a very high value, why you can say why if the you can say if I on increasing the frequency, my performance will always increase, right? But no, this is a very cost-intensive navigation stack. That as I'm speaking, my laptop is actually getting very hot because of the simulation running behind it. Right, it's actually having doing a lot of calculation. Why? Because of the lidar. The lidar is actually giving a lot of. It is actually making the laptop to go through a lot of calculations, of very intensive calculations. So if I increase the frequency more, right? So it will start computing at a faster speed, and what will happen is it will lose out. It will not be able to complete it in this particular time. Okay, so if I make it 100 or 1000, it's impossible for the laptop to do so much calculations within zero point 0.1 seconds, right? So it will fail, it will miss the update loop, and you'll get errors. You'll get warnings that it is not able to plan. So this is a planner patience, and again, this thing is when there is actually no path. You try for 4 seconds. If you're not unable to find a path, then you give up. So pendulum patience, the same thing. Planner frequency. Keep planning within 5 seconds. I guess this is a 5 second limit. You can go through all these parameters on the ROS wiki page, right? And you can tweak them and to find out the ideal behavior of the robot in a particular environment. And there are oscillation timeouts that if the robot is stuck somewhere and it's oscillating, going on oscillating, trying to get out, then after a point of time, it should start rotating. The rotate recovery package exactly is for that in navigation stack. If the robot is stuck, then just moves in a random direction, starts rotating. Right. So these are things that you can try out. Like this make our the navigation stack. The best part is it's robust, right? So if a robot gets stuck somewhere, then it won't just simply just quit live there and just sit there for the rest of the day. It will try to figure out how to get back into the mainstream. Right? It will rotate. It will try to figure out where its obstacles are. It will try to move somewhere else. So these exactly are for that. So how the robot should behave when it's faced with adverse conditions and it's stuck somewhere. So done with that, the local cosmos parameters, again the same thing. We define the global frame and the robot base frame. Be very careful about these, right? These are used almost everywhere. So be very consistent with them, right? And then these are not very important again. It's fine. So the global cosmos parameters, same thing. We have a few parameters here and there. So with that, we're done with all the parameters mostly. So this config files are very important. Okay. Because these are exactly what is controlling your robot, and changing these parameters, you will find a drastic change in the performance of your robot. So, so as you saw that I just had to launch one package for Gmapping, one for move base with these parameters inside, and I'm able to achieve what I just showed you there, right? I'm able to achieve this anywhere. I think I closed the file. Yeah. So this is one way of working with a navigation stack. I think things are very clear to you now that how you can use it, right? So another way to use the navigation stack is when you have a fixed map. Let me show that to you right now. If you're having, say, a fixed map of charge, apparently so. Just a minute. Yeah. Now, say we have a fixed map, right? A static map. We're not generating the map as we are moving. Instead, what we'll do is as we're moving, okay, I'll just show you first. The same thing again. We just launch the URDF, right? And then you launch uh, yeah. So yeah. So now if you see that I have this map, you are wondering right now why the robot is here and not inside, right? It's because it doesn't know. Right now it doesn't know where it is. Right? Like the starting point of the robot is random. So what you normally do is, I think, and these are the tasks that you have got for your camp, right? This one in particular, I guess, must have got. If you have tried with Turtlebot also, I figured. So you must be knowing this already. So do the 2D pose estimate. Just put in the apparently wherever you find it to be most appropriate for into a word, right? And then you can even give it wrong estimates. You can put it somewhere here also. It's a bit off. But as it will start moving, the AMCL algorithm will with time figure out that where it is lying and with respect to the actual map. Okay. So to show you that, now I'll just so in this method, what happens is the like just show you. So if I'm giving it an app goal right now here, as we will start moving, it will start figuring out where it exactly is with respect to the map. We will see these red lines around the robot. The more concentric those lines are, the better the localization is. I think I do not have the localization idea. If you see the AM cell comes in here, it says that AM cell pose. Those are not the variants, I guess. Mm, yeah, they have the pose added. Exactly what they're showing. So with time, it will start figuring out where it is. The more number of red lines actually the less number of red lines you see, the more it is sure of its position. When it starts moving, you will notice that it gets a little confused. It's figuring out things, but the more the point they're together, that means the more it is sure about where it is lying currently. Right. So you can see exactly where it is. It doesn't offset also. It's exactly where it is in the real world. It has by not figured out that it was initially offset by some by a little distance. and it has found out its position on the map to quite some extent, but I will still say it's not really accurate here. Now it's more sure of where it is. So again, using this, you can do the same thing. You can give it any point in the map, and it will figure out. This is more robust, as in it will not collide. Like the previous approach, there are high chances of the robot colliding also, right? Because like given the speed I had given the robot, yeah, if the robot is moving slowly, then there's no need. But this robot is actually moving at, I think, 3 meters per second. I think that is the real speed it has. Uh, let's have a look at how fast the robot is moving. So let's proceed. Okay, it's moving at a speed of 1.2. Okay, now see, apparently it got stuck. And why did it get stuck? Because it is moving quite fast. Right. So again, if you hit it, so against the wall and got tilted. Yeah. So this is what I was exactly saying. So to reduce this random behavior, right, got stuck by itself, and it's absolutely destroyed now. The map is gone. It's plain the lidar pin somewhere else. So it's kind of non-functional anymore, right? So to reduce these behaviors, you have to tweak these parameters here. So if you reduce these parameters here, the velocities, max velocities you have here, the acceleration that you're having, right? By that, you can reduce these random behaviors that you can see right now. So I'll just close it. So yeah, I think that is it about the abstract. Okay, I'll show you what the last file I launched. Right. With the second approach, the file that I launched was this one, right? Rest.launch. So in here again, the same thing you have. I have launched firstly the map, right? The map server launches the map, right? I'll tell you how I created the map also, but just hold on a bit. Just imagine right now you have the map, right? You have a map, so you have to launch that map. Otherwise, these algorithms do not know how to figure out where the map is coming from, right? There has to be a map topic. The map topic is given by this map server. So the map server is just 2 lines of code. What it needs this config file. The config file, and what is inside the config file? You have the map pgm image. Wait. You have the map YAML file first, right? It has the image. It has this image that I was talking about. This image is actually of the map itself. I'll show you. So if you see, this is the PGM image, right, of the map. This is in black and white, and it actually is it is each pixel is of 255, right? So based on that, based on the occupancy value, the black resembles that is obstacles, right? Zero is obstacles, and one means it's not occupied at all, right? So based on that, a mapping is done, and this is a grayscale image as you can see, a PGM image, right? So what does the ML file have? It has this image. It has the resolution, that is the number of pixels per meter, or meters per pixel. Yeah, it is meters per pixel. No, the way around. The origin of the thing you can keep it zero. It doesn't matter. The occupied slash negatives if you are negating the black and white. Just invert the image. So the occupied slash is the probability above which the how a map works actually is that it breaks up this image into pixels, right? And each pixel has uh, like a probability of it being occupied. So if the probability of it being occupied is 0.65, that is more than 0.65, then it's occupied, right? And it's considered to be occupied. And if it is less than 0.196, then it's considered to be free for the robot to move in, right? Free thresh. These are the two parameters that you can have here, and these just modify the map. They do nothing else, right? They will modify the behavior, the map that you will see in ROS. Okay, so if you are giving these too high values, right, then the robot will be more likely to collide with obstacles. If you're giving too low values here, then the robot will not move at all. Okay, so things are like that. So So first thing again, you declare the node, map server node. You launch the map server node, right? It has the frame ID is map, right? You don't change that normally. So with respect to which everything is defined. Then you have two more nodes. One is AMCL, right? AMCL comes up here, and another is MoveBase. Rudolph MoveBase is back again. MoveBase works with both gmapping as well as AMCL. So for AMCL again, you have certain parameters. Again, you can find it all on ROS wiki. This entire thing you can copy right from there. Just two things to be careful about: the scan topic, right? The scan topic should be coming from your RDF file itself. The the other parameters are not very important for you to know. The default values work pretty well, but you can tweak around with them based on your wishes, right? And another few things to keep in mind are these frames, right? Wherever you see frames, be careful about them. It should be coming from the URTF. The dual frame ID, it is the map. Yeah, we are doing everything with respect to the map here, right? The base frame ID is a Husky robot base link, right? The ODOM frame is a odometry, right? The ODOM frame that you have. So yeah, you can define the initial pose X and Y of the robot as well. Like what we did using 2D pose estimate, we can hardcode the values and put it in here as well. Doesn't matter. But 2D pose estimate is a GUI way of doing the thing provided by ROS. And these parameters are more or less with respect to AMCL itself, so don't need to worry about that. Then other than that, you have uh, a very important argument here. Let's move forward only. Right, so if you're giving this move forward only to move base, then only move forward. So there's some things to look about to keep in mind. Other than that, you have again move base, again the same runner views, TB local banner, because this performance is really good with Husky. The same parameter files I'm using. So these parameter files define how the robot is moving absolutely. So it's same whether if you're using it with AMCL or using it with Gmapping, right? But ultimately AMCL is used for localization itself. It's for knowing where the bot is currently. It has nothing to do with the movement of the bot, as in nothing to do with the with how the bot is being controlled by the movement spanners, right? Then you have again you pass in the velocity. The move by spotted does it actually publishes the velocities, the final velocities. It publishes to the CMD level topic, right? So you have to mention the CMD level topic. If you have used something else, you have to mention that here, right? You can mention that here. Then odometry as well. Yeah, you can tweak this like move base inside. They can take parameters like you can rename the parameters inside move base, right? Next, obviously they will have used CMD, they will have used odom, and say if you use some other topic for the same things in your URDF, you can remap them using these commands, right? For in our case, we don't need it actually because it's the same. If I remove it, it should work fine, right? But if I'm giving any other name in the URDF, then be careful to just remap them. Otherwise, by default, it uses these CMD and node topics. Okay, so those are things to be careful about. So map, AMCL, and move base, and we're done again. Right, you just have to launch one file. And yeah, coming back to how we created the map. Again, creating the map is super easy. You launch this, you launch the world, right? You launch G mapping, only G mapping, not move base. Okay, you're not launching move base here. Launch G mapping, then you launch uh, Heliopist, right? Back again. Why? To generate the map. So you can see it right now. I think we have already done it with TurtleBot, most of it. So if you move the bot around, you will see that the map is getting generated more and more with time, right? So that is exactly how you create the map. So if you actually notice here that using the first way, I got a map much faster than I will ever get by this way, right? Here I have to manually navigate, and here I have to be slow with the speed also. So the first way I will always prefer compared to this. Threading on the fly is always better. Mapping on the fly. And that is what exactly this guys are this G mapping is about. Slam is exactly, and that is exactly what Slam is, right? Simultaneous localization and mapping. Apart from that, I think we are done with this workshop. I hope you liked it. So to approach the second one, on the fly mapping and navigation. The second approach is you have a static map and to navigate based on that, right? So I'll be sharing this entire package with you so you can just have a look at how things have been implemented. Yeah, so that's it from my side. Thank you guys. I guess. चोरी मत करो यार, बहुत होगा, थक गया।